So in the last video, we did a whole bunch of U-substitution examples. In this video, what we're going to do is a whole bunch of U-substitution examples. Exact same thing. I mean, I would call these examples a little bit more challenging than ones in the previous video, but I think you'll see they follow kind of the same lines. And sometimes doing the ones that may be a little bit more challenging actually better helps you understand the algorithm you're doing in the first place. So let's give these a shot. With this first one, I'm not going to tell you immediately what U should be equal to. I want you to kind of think about it, because there's only so many options, right? I mean, you kind of make the U equal to X, or you could make U equal to 1 over X, or you could make U equal to, I don't know, 5 plus the natural log of X. I mean, these aren't the only options, but these are probably the most common ones that you'd think. But think about in each of these cases, what would the du be equal to? Up here, du would just be equal to 1 dx. Over here, what du would be equal to, the derivative of 5 is just 0, and the derivative of natural log of x is 1 over x, so I guess I'd get 1 over x dx. Over here, if u is equal to 1 over x, I think about that as x to the negative 1 power, so du would be equal to what? Negative 1x to the negative 2 dx? In other words, negative 1 over x squared dx. So I either have this option or kind of this option down here, or maybe some other option that I haven't considered yet. Which of those are going to help me evaluate this integral? Right? I have to choose u. That'll take care of some of this stuff, but I also have to take care of the dx stuff. So of my different options, this top one sort of doesn't get rid of enough stuff. If this x changes into a u, then this dx changes into a du, but I still have the natural log of x here. I mean, I guess I could make that the natural log of u, but then I haven't really simplified the problem at all. I've just changed all the x's into u's. I've changed all the x's into u's, but I haven't left myself with an integral that I'm able to take. It's not any easier than the one we start out with. Down here, when you make u 1 over x, I mean, that might seem like a good idea, but then du would be 1 over x squared dx. And there's no x squareds floating around in here for me to deal with, so I don't think that one's going to help either. However, this middle option is going to work out really nicely. Because the reason why is this 5 plus natural log of x will all just change into my u, and then the 1 over x dx is exactly what I'd have left, right? I have this 1 over x because the x is down in the denominator, and this dx. So there's not like an exact science for, in this case you always choose this, and in this case you always choose this. But if you sort of consider the different options for u and the corresponding du's, maybe you can convince yourself that the best option for u in this case is to make u equal to 5 plus the natural log of x. And guess what? Even if you can't come to that conclusion, it's okay. What you see a lot in calculus is often it's less of a linear path and more of kind of a puzzle. Like, I'm not sure what u should be equal to. Why don't I try 5 plus the natural log of x and see where it goes? And maybe I'll get stuck and be like, all right, I went down the wrong path, let me try something else, and maybe it works out. These get so complicated that you often can't tell you're on the right path until you start walking down that path. And that's kind of uncomfortable for students when they first do it. But I want to emphasize that that's totally okay, and that you learn a lot by choosing incorrect values for u when you try to do the different substitutions. In this case, we're going to want u to be equal to 5 plus the natural log of x. And with that choice, du is going to be equal to 1 over x dx. Really what I'm doing is I'm viewing this integral as 1 over x times 5 plus the natural log of x dx, instead of 5 plus the natural log of x over x. Instead of dividing by x, I'm multiplying by 1 over x. You don't have to go through and write that step, but maybe when it's written this way, it's easier for you to see, here's the du, and here's the u. I got my substitutions. When I substitute in, I get the integral of u du. The pieces fit really nicely. This is a fairly easy antiderivative to take. I think about this as u to the first power, so I want to make it u to the second power, but not just u to the second power, because the derivative of u to the second power would be 2u, not just u, so I need a 1/2 right here. The antiderivative of u is 1/2 u plus c, technically. I'm done with all the calculus, I just have to substitute back. My final answer would be 1/2 times, instead of writing u, I'm going to write 5 plus the natural log of x squared plus c. This next problem is pretty tricky. I think the substitution that you're going to want to use on this next one is you're going to want to make u equal to 1 plus e to the x. How do I know u should be equal to 1 plus e to the x? Well, think about what the derivative of this would be equal to. If u is 1 plus e to the x, then the derivative of this is, well, the derivative of 1 is just 0, and the derivative of e to the x is just e to the x. So I get e to the x dx. Look how well these pieces fit. The denominator here will all change into the u, and then the e to the x dx that I'd have left over would change into a du. When you make the right choice for u, these problems often are really easy to figure out. All I'm doing is I'm taking the antiderivative of 1 over u du. The antiderivative of 1 over u is the natural log of the absolute value of u plus c, but I don't want to leave u's in my final answer, so my final answer would be the natural log of 1 plus e to the x plus c. It's worth pointing out that you could do this problem by letting u be equal to e to the x power, because if u is e to the x power, then du would be e to the x dx. So I can choose this e to the x down on the bottom to be the u, and this e to the x dx up top to be the du, because the du has to end up on the top. But if I did that substitution, then what I'd be left with in my integral is 1 over 1 plus u du. I got 1 plus this e to the x, which I'm writing as a u, down here on the bottom. And the problem with this as my integral is this one's a little bit harder to take than this one. You probably know the antiderivative of 1 over u. It's just the natural log of u. You might not know the antiderivative of 1 over 1 plus u. It turns out that it's just the natural log of 1 plus u, but we didn't have that written down as one of our rules. So while this is correct, it's a lot harder to do it this way because you chose a substitution that left you with a more challenging integral to take. So when you're doing these substitutions, you often have freedom in terms of what you choose, but try to make life easier on yourself. If my substitution for u is e to the x, I still am left with the natural log of 1 plus e to the x in the absolute value symbols plus c. But the anti-differentiation step is a lot harder because of what I chose here. So keep that in mind when you're making your decisions. Problem C is a really challenging one. I don't think it's at all obvious what u should be equal to. I mean, it just looks like a huge mess here, right? You see this x plus 3 floating around, so maybe you're thinking that the u should have something to do with the x plus 3, or maybe even x plus 3 squared. But I don't think either of those are going to help. What might help is if you rewrite this, instead of with radicals, with exponents. So if I rewrote this in exponent form, up on the top here, I would have x plus 3 to the 1/3 power plus 1. And then down on the bottom here, I would have x plus 3 to the 2/3 power. 2 for this 2 and thirds for this 3. And maybe you're like, yeah, I still don't quite see it. All right, let me try to go one more step. Instead of thinking about this as dividing by x plus 3 to the 2/3 power, I could rewrite this as this same numerator times x plus 3 to the negative 2/3 power, right? Instead of dividing by positive 2/3, I could multiply by x plus 3 to the negative 2/3, because negative exponents just kind of mean take the reciprocal of. Maybe in this form, it's a little bit easier to see. Can you see an expression so that the derivative of that expression also exists in this expression? Think about the power rule. When I have something raised up to the 1/3 power, I bring that 1/3 down in front, and then I subtract 1 from that exponent. When I subtract 1 from an exponent of 1/3, I'm left with negative 2/3. I think this x plus 3 to the negative 2/3 will end up being your du. And this factor over here will end up being your u. You really have some options. You can either let u be equal to x plus 3 to the 1/3 power and call that good, or you could let u be equal to x plus 3 to the 1/3 power plus 1. Either way is totally fine, because tacking on this plus 1 here isn't going to change the derivative at all. If u is x plus 3 to the 1/3 plus 1, then du is 1/3 times x plus 3 to the negative 2/3 times the derivative of x plus 3, which is just 1, plus the derivative of this 1, which is just 0. So du is 1/3 x plus 3 to the negative 2/3 dx. It's hard to realize that this is what u should be, but with this realization, the pieces fit really nicely. If du is 1/3 x plus 3 to the negative 2/3 dx, then 3 du is equal to x plus 3 to the negative 2/3 dx. I multiply both sides of this equation by 3 because x plus 3 to the negative 2/3 dx appears in my integrand right here, which would be great if u also appeared in my integrand, and sure enough it does. X plus 3 to the 1/3 plus 1 is exactly what I have right here. So this u substitution will change this integral into, instead of x plus 3 to the 1/3 plus 1, I'll just write the letter u. And then instead of x plus 3 to the negative 2/3 times dx, I'll write 3 du. U times 3 times du is the antiderivative that I need to take. The 3 is a constant, so I can pull it out in front. So I got 3 times the antiderivative of u du. It's a very easy antiderivative to take. We got 3 times 1/2 u squared plus c. And we finished the problem by just changing u's back into what they're equal to. So I got 3/2 times, and then instead of writing u squared, I'll write x plus 3 to the 1/3 power plus 1 squared. And then I tack on my constant. Let's do one more and then we'll call this video good. Part D here. 1 plus the natural log of x divided by x times the natural log of x. Lots of x's floating around in this problem, right? There's 3 of them of my variable. So I'm going to have to do my substitution really carefully so that when I substitute it in, I can get rid of a bunch of the x's, but still kind of leave myself with any x's that might be necessary for the du. Honestly, at this point, when you're looking at this, you might not have any idea and you might just guess. Man, I have no clue. There's natural log of x's floating around. Why don't I try that and see if it works out? Let's let u be equal to the natural log of x, just totally blind. No clue if this will work out. I mean, that seems promising, right? That'll get rid of this natural log of x and this natural log of x. It won't deal with this x right here, but look, if u is the natural log of x, then du is equal to 1 over x dx. I think these substitutions are going to work out really nicely. This natural log of x and this natural log of x will each turn into u's, and then this x down in the denominator here, instead of thinking about it as dividing by x, I can think about it as multiplying by 1 over x, and that'll get rid of this part. What I'm saying is if you think about this integral as 1 plus the natural log of x divided by the natural log of x times 1 over x, convince yourself that what I wrote in purple here is equivalent to the original question. If you can see it this way, it might be easier for you to see how all the different pieces are going to fit in just perfectly. In the numerator here, I'll have 1 plus u instead of 1 plus natural log of x. In the denominator, I'll have u instead of natural log of x, and that'll leave me with 1 over x dx, which is exactly what du is equal to. So what I've done is I've changed this integral into this integral, which is an integral I can figure out. Or is it? Well, yes, it is an integral you can figure out, but I don't think it's obvious at all. This problem really tests your algebraic ability. What you have to do is look at this and recognize that we have a sum of terms divided by u. So I can rewrite this as 1 over u plus u over u. If you have a hard time seeing that, think about if you started right here, you have a common denominator, so you can add up the numerators to get to this stage. So in the same way you can go from this to this, you can go from this to this. The reason you want to go from this to this is in a form that's more conducive to my rules. I don't know what the antiderivative of this is, but I think I do know what the antiderivative of this is. Because look, I got the antiderivative of 1 over u, I'm good with that, and then u divided by u is just 1, I'm good with that. I could take the antiderivative of 1 over u plus 1. The antiderivative of 1 over u is the natural log of the absolute value of u, and the antiderivative of 1 is just u. So I get the natural log of the absolute value of u plus c. I shouldn't leave my answer like that because u is equal to the natural log of x. So my final answer, and this is kind of crazy, is the natural log of the absolute value of, and then instead of writing u, I'm going to write the natural log of x plus u, so plus the natural log of x plus c. I got nested natural logs going on here, plus another natural log over here, which is a pretty crazy looking answer, but the nice thing is you can always check this. Take the derivative of this guy, and I think what you'll find is that after some algebraic manipulation, we can get it to look just like this. U-substitutions are pretty wild. It's a pretty challenging method to learn, but I think typically the hardest part is just figuring out what u should be equal to. And for that, I encourage you to guess and check. Don't be afraid to get it wrong. Because each time you guess an incorrect u and you work through the problem, you'll learn why it was the incorrect u to guess in the first place, and that will make you better at guessing what u should be going forward. I know that's really frustrating from the student's perspective to not have an answer for how you figure out what u should be equal to. But trust me, any frustration you're feeling right now is shared by every single student who takes Calculus 2, and has to learn this crazy U substitution method. I got a little bit more I want to talk about with this stuff, but I'm going to save it for the last video because I feel like there's already a lot of info in this video.